This is lesson 17.2. We're going to discuss the three laws of thermodynamics. And we're going to use the third law to explain entropy quantitatively and to be able to calculate actual changes in entropy. The previous lesson, it was qualitative changes, just increase or decrease. Now we'll actually work with numbers. First law of thermodynamics is actually one you've heard before. Energy is conserved. There's a constant amount of energy in the universe. We can't create more or destroy it. So that means that all of the enthalpy that leaves a system will go into the surroundings. Delta H system equals negative delta H surroundings. Or everything that goes into a system came out of the surroundings. You're not gaining or losing energy overall. It's just moving from one place to another. So all the energy transferred out of a system goes into the surroundings. Now for the second law, entropy is not conserved. We don't have a constant amount of entropy in the universe. Instead, the entropy of the universe is always increasing. Overall, the universe is always getting messier. Delta S universe is always a positive value. And delta S universe equals delta S system plus delta S surroundings. So the entropy change of the system and the surroundings, everything around it, add that up, you have the whole universe. That value, delta S universe, always has to be greater than 0. So that means delta S system does not equal negative delta S surroundings, except at equilibrium. And we'll talk about that point in a minute. But in general, what this last statement is trying to say is that entropy is not conserved. So a process that allows the entropy of the universe to increase is thermodynamically favorable. That's actually the real criteria for whether or not something is thermodynamically favorable. We said in the previous lesson that in general, if it's exothermic, and in general, if the entropy of the system is increasing, that it would be thermodynamically favorable. What we really want to focus on is that the entropy of the universe, not the system, but the universe has to increase. And we will pick up this point again in the next lesson and get more specific about that. But that right there is kind of part of the second law as well. So if the entropy of the system is negative, meaning that S decreases, the system is getting more organized, then the entropy of the surroundings has to increase. That delta S would be positive, and it's going to have to be larger in magnitude than the change of S in the system to compensate for the fact that the system got more organized, its entropy decreased. So if the two terms added up are always going to be a positive value, then when delta S system's negative, delta S surroundings has to be positive and bigger. So if you make your system more organized, your surroundings are going to have to get even messier to allow for the process to go forward. So I mentioned equilibrium as a special point. So looking at that special point, here delta S universe actually equals 0. It's not greater than 0, it equals 0. And that will mean that delta S system equals negative delta S surroundings. What this is saying is that at equilibrium, neither direction of the reaction is thermodynamically favorable, which you kind of already knew that. At equilibrium, it's not going to shift left or right. You're at equilibrium. It's staying where it is. However, because we're at dynamic equilibrium, both reactions still occur simultaneously. It's just that no one is going faster than the other. Their rates are the same. So they're both occurring, but you're at equilibrium. You don't have no net change in either direction. Therefore, the entropy of the universe is unchanged. Even though both reactions are happening, the net change in the entropy is 0. So that's why delta S system equals negative delta S surroundings at equilibrium. Kind of contrasting entropy and enthalpy for a minute. You know that delta H means, is it endothermic or exothermic? It means heat is being transferred in or out of a system. Delta S means that the entropy is increasing or decreasing. It means matter and energy are being rearranged. But entropy was not transferred. Entropy is not a thing to be moved around. It's not mass, it's not energy. Enthalpy is energy. So we think of it as a thing that we can move from one place to another. Entropy is just a measurement. It's an evaluation of how messy a system is. So when it is changed, matter and energy get rearranged in the system or in the surroundings, but they aren't transferred from one place to another. Entropy is not transferred. So that kind of goes along with we're not trying to say that the entropy leaves the system and goes into the surroundings. That's just not really a thing. So delta S system does not equal negative delta S surroundings, except at the special case of equilibrium. We know from the past that we can't know or measure an absolute value of H. We can only measure the heat that's transferred, the change in H, delta H. Before and after the heat's transferred, we can figure out what that change was. So we always talk about delta H. We can, however, measure an absolute value of entropy. We can say how much entropy is contained in a chemical. Contained is not a great word, but I can't come up with a better word for it. How much entropy does that chemical have, or does that system have? What's the measurement of its organization? We can get an absolute value of that. So that brings us to the third law, which says S equals 0 for any substance as a perfect crystal at 0 Kelvin. So think about what 0 Kelvin means. Absolute zero of temperature. It's as cold as anything could be. It means that we have no energy, no vibration, no movement. If you're a perfect crystal, that's the most organized a system could be. Everything is perfectly lined up. So that should make some sort of sense to you that if you are a perfect crystal with no movement and no energy, no velocity, no temperature, then that's the most organized any substance could be. So we don't have to pick an arbitrary reference for S like we do for H. Remember we talked about altitude and we said you needed to pick a reference for the altitude or the height of a mountain. We picked sea level. We could have picked the center of the earth, but we had to pick something. We had to pick something for H. We don't have to pick something for S. There is an absolute zero for entropy, and it's at 0 Kelvin. So the reference point that we picked for enthalpy, for H, we said that the heat of formation equals 0 for pure elements at standard conditions. And standard conditions was 1 atmosphere for a gas, 1 molar for an aqueous solution, and they're usually assigned at room temperature, but temperature is not part of standard conditions, it's not specified. S does not equal 0 for elements at standard condition. S equals 0 for any substance as a perfect crystal at 0 Kelvin. Definitely not standard conditions. 0 Kelvin is much, much colder. So looking at these values of entropy, I gave these to you in the last lesson as well. These are absolute values. Notice it doesn't say delta S, it just says S. It's just S, entropy. It's not a delta because there is an absolute zero. So we don't need the delta. When we talk about heat of reaction, we never know the enthalpy of the products or the reactants. We never know that number exactly. We use Hess's law, we use heat of formation, something like that to get heat of reaction. We have to have that reference of the heat of formation at standard conditions. But we can calculate this exactly. We can get delta S for a reaction by knowing the enthalpy of the products and subtracting off the enthalpy of the reactants. We can look up those numbers exactly. So to calculate the standard entropy for a reaction, here's the formula. This formula is on your constants and formula sheet, and it should look familiar to you. It should remind you of another formula you've already used, because you used something very similar for enthalpy. And notice the difference here is that for entropy S, it just says S, but for enthalpy H, it says delta H. So note that the delta S reaction here, that's what we would call delta S of the system. The surroundings would be the surroundings around the reaction. And just pointing out again, we don't have delta S, F for formation, delta S, not F. We don't need that. We have absolute values of S, so we're not talking about entropy of formation the way we did enthalpy of formation. I want you to do two classwork problems now. They're both printed in the packet. The information at the bottom there in yellow, though, is not printed in your packet if you want to make note of that. You're going to get the data from Appendix 3. That's the end of the textbook. And these should be fairly straightforward because you've already done calculations like this for delta H. But if you need help, look at example 18.2 in the book. That's page 809 in the electronic edition of the book. This would, of course, be chapter 17, example 17.2 in the hard copy of the book. Here's your second problem. When you're looking up the entropies in Appendix 3, there's a separate table for organic substances, like CH4. So it's a little harder to find, but just keep scrolling through Appendix 3 and you will find it at the end there. So once you are done with all of this homework, or classwork, sorry, take a picture of your work and email me the answers.